All right, so I know you're probably a little lethargic now after eating lots of cookies, as I did. But this is going to be a really cool talk because this is on not just science, but also science and pretty pictures. And if you're giving a presentation, you know, half the audience is there for the science, but half the audience just wants to see what cool visualizations that you can achieve for your computational simulations. So this is very useful. And this talk is going to go directly into Sam Skillman's talk, and he's going to be getting into advanced volume rendering. So this is just the basic stuff. So I'm going to give a little bit of introduction, but then most of this is going to be a kind of a lab where you can start playing with this on your computers. So anyway, okay. So what is volume rendering and an off-axis projection? Because I'm covering both. Because at some level, they're the same thing. It's just a different transfer function that you're using. And for reference, there's a website that's on the bottom of these slides that has information and basically the full algorithm that's followed in the code. But if you need to access it later. So really what's going on is we're numerically integrating the radiative transfer equations for a given volume. Obviously, we're all using grid-based data. And so you take the grid, the full volume that you want to render. You start in the back with an empty photon, and then you let each photon from the back that represents a pixel travel through your different grid elements until it gets to the front. And it takes into account absorption and emission of the gas and the particles intervening, depending on what transfer equation you're using. For the most part, we're just doing emission. We're just doing gas as an emitter of light, although it does have the potential to act as an absorber as well. So let's volume rendering. For the most part, when we say volume rendering, we refer to using a particular transfer function called the color transfer function. Whereas when we're dealing with the off-axis projections, that's like the projections we were doing before yesterday that Stephen and John were taking us through. But off-axis obviously allows you to have an arbitrary angle at which you're projecting onto. Okay, so so this last image, this image itself is an off-axis projection from one of my galaxy simulations. Whereas this is a volume rendering using an isodensity contours to represent, well, the distribution of mass throughout the simulated volume. So the yellow representing a certain density level, whereas the green represents a higher density level, and so on and so forth. Okay, so let's get you guys started. The first thing I want you to do is type into a command line in the directory outside where you have gas sloshing present. So you'll be in the directory where there's a gas sloshing directory and then a subdirectory of gas sloshing, and then this sloshing nomag 2. Sorry, there are so many ridiculous parts of these file names. But what I want you to do is at the command line from that external directory, type this entire thing in. Now what you're doing as you type this in is running something that we haven't yet introduced, and that is YT has a number of command line options where you can type YT and then some command, whether it's analyze or render or hub submit or paste bin, which you guys have seen, paste bin grab. Well, there's also render, and render does just kind of a volume rendering default without having to make a script, and it has defaults set that are relatively intelligent, but we can set these with other flags, like contours have 10 isodensity contours, enhance, where you kind of bring out the colors, and so on and so forth. So you should render something that looks like this in about 20, 30 seconds or so. So has anyone done that so far? Is anyone in the midst of rendering as we speak? Okay. Well, let me know if you guys get something that looks like this really cool image that we see here.
How many people have volume rendered with YT before?
Oh, that's pretty good.
And how many of those people, how many knew about the YT render command?
Yeah, I didn't. You aren't necessarily going to need gas sloshing for the other examples that I do. Just look on with somebody else for right now.
By the way, this works just fine with the isolated galaxy.
Yes.
You just replace gas logic with that. It works. Looks great.
Okay. Yeah. If you want to do it with the isolated galaxy as your file name, as your data dump, instead of gas sloshing, it should work. And then also with all the command line options at YT, you can do YT, the command line option, and then -- help to see all the different flags and parameters that you can set associated with that. And that works with any of the command line options. And if you want to see what command line options are, you can just do YT space help, and it lists all of them with a brief descriptor. But we'll get into more of that tomorrow to explore some of those. Those are the options. So have people been able to do this on their computers, and you guys are getting something that looks reasonable, that looks kind of eye-popping, looks kind of cool? Yeah? Over here as well? Your eyes are going to be popped. I'll use this laser. What's that? Do you want to, what? Oh yeah, you can do that. That's right. Using the other command line option, the upload image option, to throw it online. What's the URL?
I'll paste it in the, whoops. There you go.
You have to give it to me.
Oh, I have to give it to you? Integer, ET, capital L, capital N, lowercase j.
Capital N, lowercase j. Ta-da! What.png, very nice. Yeah. Mild applause. All right, so, okay. So what you've just done is you've done your first, well, maybe not your first, a volume rendering using just these commands. And it's pretty straightforward. We use 10 isodensity contours. We use this enhance parameter, which we can talk a little bit more about. We set the width of each isodensity contour to be 0.3. No, the width is the width of the volume. I'm sorry. The width is the width of the volume across here. So 0.3, since it's in units of unitary, that means 0.3 in simulation units. So it's only using 30% of the volume. By default, it's centroids in the very center of the simulation, and it's 256 by 256 pixels. Obviously, as you increase the resolution, it takes longer to run. So I just set it at 256 so we get this, and then it outputs to this volrend.png file. Okay, so that's pretty straightforward. But there are a lot of options that you can explore if you do YT render -- help. But let's get past that. Let's get into some actual scripts, because you're not going to be doing like stuff for publications at the command line. You want to do some scripts so you can save it. All right. So for the scripts, I need you to grab a couple of things using the YT pastebin grab command. These various different pastebins. So, and then I'm just having you pipe them into individual Python scripts. So again, from that same directory, the external directory in which your data sits, run these commands. I'm sorry, it's a little tedious. But this will give you the 4 scripts that we'll be able to play with a bit and follow along and be able to do some cool volume renderings and off-axis projections. So I'll give you guys a minute or so to get all that. You got them, Sam? No. All right. This is where read line is your friend. Does everybody have these? No. Okay, sorry. Don't mean to rush things. Yeah, you got them, Britain? Okay. Does everybody have these now? Does anyone not have them? Okay, awesome. What? You don't have them? What?
I found an error with volume rendering.
Oh, really?
Yeah.
Uh-oh. Oh, no. Is it significant? Does it break it?
Yeah, but we'll talk about it later.
Okay. All right. So, well, I want people to run this, so if it's going to break, I didn't have any problems when I ran it.
It says the camera object has no attribute par rank.
Par rank. Have you pulled, do you have a recent, wait, Matt, when you run it, do you get the same issue? All right. Well, I guess we'll find out in mass here pretty soon. Will people just run python volrend.py? It works for you? Okay, good. Then Jeff Awishi, it turns out, is broken and not the script. All right, so what it should give you are two files that it outputs. It should give you DD0046 transfer function and DD0046 volume render. I'll talk about that in a second, but I want to make sure that people have this. So if you don't have this, this is a bit like a lab in that, you know, raise your hand and Stephen or Britton or Matt or Jeff or somebody will come over and assist you. Now this is all contingent on having the Galaxy, what's the data set? Galaxy, oh, this is, you're right, this is Enzo Tiny Cosmology. I chose it just because it was small and it doesn't take very long to render. Are people getting out something that looks something like this? Are you guys getting something that looks like this? Okay, good. You're what?
I'm still in the first render. I haven't gone through it yet.
Oh, I see, I see. On the command line stuff.
Yeah.
Okay. Oh, do you not have then the, did you not get the paste bin grabs of the, did you get these?
No, I can do it.
Okay. Sorry. Don't mean to rush. So while you're waiting, if you want to look at the off-axis, the volrend.py is identical to the volrend verbose.py, but as you may guess, the verbose version has a lot more text. It has a lot more in terms of comments to describe what each step is doing, which we're going to go through here. But while you're, while we're waiting, and it also has lots of other options that I've commented out inside dashes, so you can switch up which data set you're looking at. You can switch up the ISO contours. You can switch up this and that and the other. So that's what I was going to have you guys play with. But while you're waiting, if you're impatient, you can start looking at that as well. Do you guys have it? Okay, sweet. Okay, so what we're looking at here, what's happened is we took the mini cosmology simulation and we did a volume rendering of it with 6 different ISO contours. Now what does that mean? Well, we're looking at the density field, although there's nothing that ties us to necessarily looking at the density field. But it makes sense at first level if you want to do a volume rendering. So we're looking at ISO contours in the density field, and our density values vary from 10 to the negative roughly 32nd grams per cubic centimeter to 10 to the negative 25th grams per cubic centimeter. So that's what here on the on our transfer function map, these are the values of density. And there's this really cool command in the code that automatically generates these different Gaussians to put them in that transfer function, so that whenever a photon encounters density of that particular value, it gives it a color associated with it. And the height of it is essentially the alpha. That's the brightness of that particular feature. And the reason these are going in increasing intensity, as you can see here in this nice, nonlinear curve, is that you want to be able to see the stuff inside other isodensity contours. So you have to make the stuff inside brighter. The stuff inside has a higher density, and so it needs to have a higher transmission rate. Does that make sense? Okay. On the right, we're just seeing the visual representation of that. So let's actually look at the code, because it's a lot more interesting than just listening to me. Oh, I don't want to do that. Okay, so this is what you guys should all have. If you want to open up, I just opened up volrend.py. So we do our normal imports. We identify, say the file name, which is, actually, I'm going to take a note out of Jeff's book here and use this. so everybody can see. So this is the file name that we're looking at. We load it up. We want all the data, so we're not just looking at some sort of small data object like a sphere, but we could be. We're just by default using all the data. We define the minimum and maximum for the density across all of that data, which is to say the extrema of the density. But again, we can do it for other fields other than just density. We could do it for temperature or bulk velocity or something like that. We want the log values. This is NA just represents numpy, so it's take the log base 10 of the minimum and get out its log, and maximum get out its log. And then we define this thing called color transfer function, which is essentially this transfer function object, which, as we see here in our plots, defines the alpha and the colors associated with building up the radiative transfer through our volume. And we run this command called add layers 6 with a width of 0.02. So that's what defines these 6 different peaks with a width of 0.02 in the Gaussians. And then I just plot it up. You don't have to plot it up, but just for the pedagogical purposes here, we plot it up. We define a center that we want to project to. We define L as an angular momentum vector. It's not really angular momentum. It's just our projection vector, the width of the volume, and then the number of pixels that we're having in that. And then these are just some print statements that I've included so we knew what the heck was going on. And then you use this nice function called camera, pf.h.camera, where you include the center, the projection angle, the width, the transfer function, and the resolution. You take a snapshot of it and you write it out. So it's pretty straightforward, right? This image object, oh yeah. So how do you define up? Up is the L value. Oh, I see what you're saying. How do you define? Okay, that's something that, what's that?
You can optionally specify it with up equals some vector. Okay.
Yes. We're going to get a little bit more into that when Sam's talking, because this camera interface, which we've only just touched upon for saying cam.snapshot, can actually allow you to move around that. You can specify a north vector. You can specify all sorts of things to rotate around a particular object or zoom in or pan. So there are a lot of options that we can go into, but here, just as a really basic demonstration, we don't specify that. Is everybody cool? So this image object is simply a numpy array. So you can do other things with that. If you wanted to drop it into some sort of other plotting function that you like or whatnot, it's 3 dimensions in terms of its I guess our pixel here, we're doing 350 by 350. So it's a 350 array by 350 array by 3 different values. One for red, one for green, one for blue in terms of the intensity. So you can do other things with that. Okay, so that was all fine and good. So let's do something more fun. Open up the volume render verbose.python on your terminal. And what I've done is I've included a bunch of different options for what you can plug in there to do different volume renderings with some of the different data sets. So there are the different file names of the different data sets that you can plug in. We load up all the data. You could do the min and the max and plot up what temperature looks like if you want to as your transfer function. So anywhere that I've included these dashed lines here around options, and I've commented one or more of them out, feel free to play with that. And in fact, if you guys have data sets on your computer right now that aren't part of the Enzo set, feel free to use those as the file names and actually use this on your own data, because that's what this is all about, is getting you guys more familiar with how to use these tools with your own stuff instead of using it with our canned data sets that we gave you. So feel free to do that. So let's continue down. You can add different numbers of layers, different widths. of each layer. You can use different color maps, as you can see here. I've also included a couple of other functions: sample, color map, add step, and add Gaussian. So you have more control over, instead of just I want to add n Gaussians to the isodensity contours, you can add a step function to the isodensity contours, or you can add a Gaussian of any arbitrary color. So this is a red color because it's only using the red channel: red, green, blue, and then the alpha for the intensity. But feel free to play around, and especially given that this is set up to only use 350 pixels, 350 by 350 pixels. It shouldn't take too long to render on your computer, maybe 10 to 30 seconds or something like that. If it's taking too long, then you can drop that number for n. You can specify a different center. You can have it find the center of mass, or find the max in density as your center. So just uncomment that line out. If you wanted to look down the angular momentum vector, if you're looking at a disk galaxy or something like that, use that as your L vector, this projection direction vector. The width of the volume that you're rendering. By default, we're just using 1, so it's the entire volume. But you could go larger than that, so you can actually see the edges of the volume, which can be useful, as you'll see in some of these rotation movies that we're going to see. You can do a smaller region. You can even do it, instead of doing in simulation units, you can do it in kiloparsecs or megaparsecs, just by specifying what I've done here. This is in 5 co-moving parsecs, because it's 5 divided by the parameter, what the parameter file thinks is a kiloparsec. Yeah.
I'm curious. So you have a width and then a vector. How far away is the camera from the center?
Good question. The width. What's that? Yeah. So the width effectively determines. Oh, so the question for the camera and for the rest of the audience is, we have a width and we have a vector, but how deep does the vector start out? Like, how far out does it start? And it's defined by what that width value is. If you define a width of 0.2, it basically cuts a volume that's 0.2 on a cube that's 0.2 on a side, and then it renders through that. So you aren't going to get the overlying stuff. You're not going to get this long column of stuff. You're just going to get that cube in the middle. There is a way to do that. Instead of at the beginning, I specify dd equals all data. Up here at the top, dd equals pf.h.all data. You could specify a smaller volume, for instance, to look at a sphere or a column or an arbitrary size prism of material, and then have the width be an arbitrary thing, and you'll go through that entire depth. Is going to be messed up because you'll get the outsides.
You can't render a data.
Yeah, you can. Instead of using dd, you could do dd equals pf.h.sphere.
Where's DD?
Oh, maybe you're right. Where is dd used later? It's used for the transfer function? Oh. Oh, well then maybe we don't need that there.
You can only render,
Because I'm not using the arbitrary transfer function where we define it within the...
right now you can only render the full volume or a smaller cubicle volume. So
That's right.
that's a project that will hopefully be on the top of someone's list.
So for those of you who didn't hear, right now you aren't able to render a sub-volume very effectively with an arbitrary sub-volume, I guess, is the question.
But you can zoom in such that you're only looking around that area.
That's true. So by playing with clever uses of the width value, you can do that, but you can't get these long columns of data.
It does not have to be cubical. So you could specify 3 widths. You can essentially render any subvolume that is, you can render any subvolume that's a rectangular prism.
Really, so width can just be a 3-element array. Okay, so you can specify a width that's a 3-dimensional, or three-valued array.
If it covers Windows raise stop tracing.
Okay.
The raise trace for
Okay, so it designates when rays stop tracing. All right, so let's keep going here. So are people like playing with this and getting cool stuff? I hope, because that's what this is all about. Please feel free to play here, to manipulate this and modify it to your heart's desire. Then finally, at the bottom, when we're actually doing the pf.h.camera call, the default thing that we were doing doesn't have, you can see a couple of things here. Fields, by default, it is density because generally people want to volume render what the density field looks like, but you could do temperature, you could do any arbitrary field. In fact, you can also weight by different fields. There's the no ghost, which is, if no ghost is set to true by default, it basically doesn't load up the ghost zones in your data. So you can sometimes get artifacts in your data, but it's quicker. So if you run no ghost equals false, your your images are going to look a little bit cleaner, but they may take a bit longer to render. The ghost zones. I think it just reads them. The ghost zones? Right.
So if the ghost zone don't exist and it doesn't have any interpolation from the boundary volume, it still gets to it. If you ask for, if you use the default behavior, and the default itself has been a subject of some, but if you use the default behavior, what it does is just in some data sets. But many data sets it's okay.
Many data sets it's all right. So you can play with that and see what effect it has on your data sets.
Can you remind me how you change
the width of the entire volume that you're projecting? Just change the value of W. So it should be higher up in the description here. So just after the designation of the center and the projection angle, if you look at W, you can set it to be 1 or less than 1. Or you can also set it to be dependent on, some sort of physical unit like kiloparsecs or megaparsecs. And your question? Oh, so the question is, can you do multiple fields simultaneously? So have like one density and temperature. Can you? You can. So you could have a single projection or a single transfer function that gets a Gaussian added for temperature and one added for density?
Yes, in different colors.
Okay.
John actually did this. I was able to show it the other day, don't you?
Okay.
Well, you're talking about the width one.
Yeah. So that was a script that Sandy and writing two separate volume rendering. Oh, I did do that. So you can do this. It's not. So
I'm trying to get him the mic because he keeps talking.
Basically, what you can do is you can set it up so
Just give it to him. It's tricky. Okay, so make sure, though, if you're doing the fields equals something other than density, that you also do the transfer function. Have the bounds of the transfer function be on whatever field that is. So if you change the value here to be cam equals pf.h camera fields equals temperature, you need to go back up to the top where the transfer function is and make sure the transfer function's limits are set from the temperature and not the density, because you're going to have different isocontours dependent on the field. This is what we have. That's a beautiful image. So it's a beautiful image. One thing is, as I specified in the scripts, you can specify this thing called clip ratio when it runs a snapshot. Now, clip ratio has different behavior in different contexts. Sometimes when you use clip ratio of a smaller value, it will effectively cut off the brightness values, shrink the overall intensity of your image to be only 2 sigma off your brightest value, and so on and so forth. Sometimes it is more effective than other times. So off your minimum value, okay. One of the things that Sam is going to cover in the advanced session is well, I think he's going to cover, is this function called enhance, which allows you to go to brighten your images a bit. Okay, so with that, I just really want to quickly cover off-axis projections. So can you please run python offaxis.py on your data, just in your command line, and you should get an image that looks something like this. Is anybody getting something that looks moderately like this? Okay. You get what? Oh no, errors. Does any? Okay, it's working for some. So what's the? Can I have some of the lab TAs to help out for people who are receiving errors? So if you're receiving an error, can you raise your hand?
I know why.
It gave me an error until I changed the data path.
Yeah.
Oh, okay. So it was simply that it wasn't pointing to the right data set. Okay. Thanks, Britt. Are you guys able to render something that looks like this? So what we're looking at is a column density map. Instead of dealing with these isodensity contours or isocontours, it's a column density map of the same volume from the same projection angle. That's why it looks pretty similar to the isodensity contours. But it's just increasing the, going up the color map with the increasing column density of material. What's interesting is because we're doing the entire volume and we're from an angle, you can see vignetting at the corners. See the vignetting? Because we're projecting it from off the angle of the axes, and so you get a little bit of void there because it's coming off. So has everyone been able to run that and produce something that looks like that? No? Yeah? Okay. Okay, so for this one, again, go ahead and play with offaxis _ verbose. Oh, I guess I haven't even really defined. It's a very similar script. It's actually even simpler. We define a center. We define an angle of projection. We define a width and the resolution. And then we just run this function called off-axis projection where we plug all those in. We plug in a field. You can specify whether or not you want the ghost zones included. And then you write that out. Now, there's something interesting here. When you write it out, you take the log of the value. Because we don't have to deal with the transfer functions and such. Under the hood, in off-axis projection, we're actually making a projection transfer function to deal with this. But this kind of, it covers over that, and it makes it easier to use. I've also included this function called right projection, which makes a nicer looking version of this, depending on your opinion. It includes this version, which actually has the color bar associated with the column density map on the side. And it allows you to specify a title, that sort of thing. So if you look in the verbose file, in off-axis verbose, again, it gives you lots of different options to play around with the different data sets and to generate generate different things. So it's almost all the same as with the volume rendering, but here you can include a weight to your off-axis projection. So like do temperature weighted by density, and here you can specify the color maps. Instead of in the projection function, you can specify it in the when you call write image on the data. So you could do it to a variety of different color maps. So please feel free to play around with this. And I won't be showing any more through the Imager interface. So, all right. Well, feel free to play on this for a couple of minutes, because Sam will get started in a couple minutes and play with the camera interface.